Now we're going to develop the equation of state. So the equation of state tells us about properties, just related to properties of the fluid. The one you're most familiar with, and the one that comes up actually the most when it's needed, is the one for ideal gas. So of course, airflow, as we know, is an ideal gas. A lot of fluid mechanics problems in engineering involve airflow, or can be approximated as airflow. So for compressible flow, that is for things that are not incompressible, that means that the velocity is either fast, so that it's higher than 0.3 Mach, 0.3 the speed of sound, or there are large t variations in the flow. We use the ideal gas law. So P equals rho RT is the equation of state. So that is the canonical equation of state that I invite you to think of. When you think of equation of state, think of the ideal gas law. It relates properties to each other. However, as we have said countless times at this point, we often have incompressible flow. For incompressible flow, the equation of state is really boring, and we really just kind of ignore it. It's rho equals constant. So that is the equation of state for incompressible flow. Barely even counts as an equation. So in incompressible flow, we really don't use the equation of state. As soon as we make the statement it's incompressible flow, rho is a constant. Somehow we have to find rho one way or another, depending on what the flow is. Sometimes we use the ideal gas law to find rho, so that can be the case. But if there aren't large t variations, rho can still depend on pressure. But now we've said rho is constant, so we're just going to find it for one part of the flow, and then it's true everywhere. So that is the equation of state. If you have that as your equation of state, if rho is a constant, then we can look back at our conservation of mass equation and change it. So here's our conservation of mass equation, or our continuity equation in general. And we said this was true for all flows, and it is. So it should be true for this one as well. But of course, it's going to get simpler if rho is simply constant. You could think maybe it just goes away, but it of course doesn't go away. We need it. So it simplifies though. So if rho is constant, then of course this term is going to go to zero, because d rho dt will be zero. Rho can't be constant if it's changing in time. So that just leaves us these other three terms. These other three terms are derivatives of rho u, and rho u, rho v, rho w, but rho is constant. So I can pull constants out of derivatives. So that means that the equation of state will look like this. Right? So rho du dx plus rho dv dy plus rho dw dz is equal to 0. But that's pretty silly. I can divide everything by rho. So we can just say this is equal to du dx plus dv dy plus dw dz is equal to 0. So I divide everything by rho, and that just goes away. So this is in fact our equation, our continuity equation, or our mass conservation equation for incompressible flow. Just to make a mathematical point here, so I'll have your attention. If you go back to this form of the equation, d by dx rho u plus d by dy of rho v plus d by dz of w rho equals 0, and you were to apply the product rule to that, so you would have u d rho dx plus rho du dx plus v d rho dy plus rho dv dy plus w d rho dz plus rho dw dz is all equal to 0. Well, okay, but d rho dx, well, rho is constant, so that's 0. And du dx still exists, rho is there. d rho dy, rho is constant, that's 0. And dw dz is fine. d rho dz, though, rho is constant, that's 0. So we end up with exactly the same thing, du dx. That's why you can pull constants out of derivatives because this is what happens. Those terms with d rho dx, d rho dy, and d rho dz just are zero because rho is constant. So we end up with the same thing. So this is our mass conservation or continuity equation for incompressible flow. So for incompressible flow, that is our mass conservation continuity equation.